Well, welcome back. We are now in part D of chapter 17. On this part, what we are going to do is to begin using quantitative analysis of acid and bases. In other words, we're going to start using formulas and math. And let's begin with a problem like this. Or actually, these are the objectives, sorry. So what are we doing? We're going to be finding the hydrogen concentration. We're also going to be finding the hydroxide concentration. And once we do that, we are going to be finding the pH and the pOH of the solution. Remember, all these acid and bases are aqueous solutions. Excuse me. So let's begin by recognizing the formulas we're going to need. You already know Kw. Kw is nothing more than the concentration of hydronium multiplied by the concentration of hydroxide, and at 25 degrees Celsius, Kw is going to be 110 to the minus 14, no units. It's a equilibrium constant, so there's no units. So once we do that, if we can find the concentration of hydronium or hydroxide, then we can move to another set of formulas, pH and pOH, where the P is nothing more than the minus log of whatever we're doing. On this case, we're doing the pH. H is for hydronium or H plus, so that's nothing more than the minus log of the hydronium concentration, and we use molarity. And you can do the opposite. If you're given the pH, then you can use this formula to find the hydronium concentration. And if we apply the logarithmic function, or the p, to the Kw, we're going to see that this becomes in a format like the one presented. And when we apply the rules of logs at the value of Kw, we come up with this formula, which is super important also. So what we are going to do is to interrelate these formulas to attack every problem that we're presented with. So let's start with this problem. We are asked to calculate the hydroxide given the hydronium. What formula can we use? Hydronium hydroxide, they are related by Kw, so what we know is Kw, which is 1 times 10 to the minus 14, equals hydronium times hydroxide. Since we know that 110 to the minus 14 equals the concentration given for hydronium, 9.7 times 10 to the minus 9 molar, multiplied by the concentration of hydroxide, then all we have to do is use a simple math operation, get rid of the hydroxide on the right side by doing the same on the left side. That takes care of that, and that tells me that 110 to the minus 14 divided by hydroxide gives me that, which doesn't help me at all. That's not what I want to do. So we go back to square one. Obviously, that wasn't what I needed, right? What I need to is to get the hydroxide by itself. So what I'm going to do is I'm going to divide by 9.710 to the minus 9. And I'm going to do it on both sides. Which tells me this will cancel. And my solution becomes then 110 to the minus 14 divided by 9.710 to the minus 9. That will give me what I'm looking for, the concentration of hydroxide. And that's going to be 1.0 10 to the minus 6, which is just a matter of putting this number on your calculator. So once more, how do you relate hydroxide, the concentration of hydroxide and the concentration of hydronium with the Kw formula, which is this one right here. So that's the formula that we use for that problem. And remember, you do not have to memorize any of these formulas. Hopefully, by using it so much, you will become very familiar with them. And if 10 years from now you need to use them, at least you will remember there's a formula you can use, and all you have to do is know what to look for on the internet. If we still have internet 10 years from now, you probably have a microchip inserted on your brain, and all you have to do is blink your eyes. So what about this problem? Now we're being asked to calculate the pH. So how do we calculate pH? Looking at my formulas, here's one way to calculate pH. So if I do the log of the hydronium, I get pH. Here's another way to do pH. If I know the pOH, then I can find my pH. So that would be another way of doing it. And yeah, so we had those two possibilities. pH equals the minus log of the hydronium, or if we know the pOH, 40 minus the pOH equals pH. So let's see which one we need to use here. Well, we're given the hydronium concentration. So therefore, pH equals minus log of the hydronium concentration given. Just plug it in on your calculator, and you should get a pH of 8. And then based on that, we are asked to decide if the solution is acidic or basic. So here's the scale. Anything below 7 is acidic. Anything above 7 is basic. And right at 7 is neutral, just like water, or like water is supposed to be. So given that we found a pH of 8, that's going to be basic. So that's all you have to do. Recognize this scale. And be able to figure out which is which. So with that in mind, you can go ahead and do the daily work 17.8. So you're asked to calculate the hydroxide and to classify as either acidic or basic. Or neutral. It could be neutral also, right? Now let's do this problem now. Once more, we are asked to find the pH. So we know that pH is going to be minus log of the hydronium concentration, or pH equals 14 minus pOH. So those are the two formulas we can use. And the first one we get is what would be the pH for a solution that have this concentration. And the first thing you have to do is realize what you're dealing with. So we have 0.028 molar hydroiodic acid. And then you have to remember this. HCl, HI, HBr, H2SO4, HNO3, HClO4, and HClO3 are my strong acids. And a strong acid means that it breaks 100% into the ions. So if you have 1 molar of any strong acid, you're going to get 1 molar of hydronium when you place it in water. So a strong acid, the concentration of hydronium is going to be exactly the same as the concentration of the strong acid because it's going to dissociate 100%. Therefore, we call them strong acids because they go 100%. So that means we don't have 0.028 of HI, we have 0.038 of hydronium. And then we just plug it there and we can find the pH. What about the second one? Second one is another strong acid. So we're gonna have that concentration of hydronium and we just plug it there also. So those two are easy. So let's deal with the other ones. The other ones are gonna require a little bit more critical thinking. So those two, you know how to do those. What about this one here? You got 0.055 molar in perchloric acid, which is a strong acid. So we know we have 0.055 molar of hydronium because it's a strong acid. And 0.028 of another strong acid, so you also have 0.028 molar of another strong acid producing more hydronium. So since both of them are part of the same solution, in reality you have 0.083 molar of hydronium. And all you have to do is plug it into the formula and you get your pH. So the hydronium concentration is additive. Any strong acid is going to be producing hydronium. We don't care where the hydronium is coming from. We just care that we have that much hydronium altogether inside that solution. What about the next one? For the next one, you have a solution that is 0.0 molar in perchloric acid. So in reality, you have 0.0555 molar hydronium because it's once more, a strong acid. And 0.028 molar of a strong base. So to be a base, to be a strong base, you have to have a metal and hydroxide. Do we have hydroxide? Yes, we do. Do we have a metal? Yes, we do. We got sodium. And in addition to that, the metal has to be from group 1 or group 2. Sodium is on group 1. And if it happens to be from group 2, it cannot be beryllium or magnesium. So anything from group 1 or group 2 except beryllium and magnesium. So we definitely have a strong base in there. So do bases produce hydronium? Hydronium? No, they don't. This base is going to produce instead hydroxide. So what happens when you put a acid and a base together? They neutralize each other. So the neutralization is 1 to 1. So for every 0.028 of the base, you're going to consume 0.028 of the acid. In other words, you're going to find the concentration of hydronium, which you already know, and you're going to subtract what the base is consuming. So when we do that, you're going to get 7 to... So you're going to have a hydroxide being the limiting reactant indicates that the excess reactant is going to be hydronium. So that's how much you're going to have left after the reaction is complete. And then you just plug it into the formula. So you got to be careful what's on the solution. Are they neutralizing each other like on this case, or are they combining like on the previous case? And then we're going to close this discussion with something a little bit more challenging, which is material you learned in chapter 14 dealing with concentrations. So we have 1.85% mass of ACl, meaning we have 1.85 grams of hydrochloric acid for every 100 grams of the solution. That's how we do the percent mass, right? It's always, except for molality, it's always solute over solution. Molality, remember, is solute over kilograms of the solvent. So we're dealing with percentage. So a percentage translate like that. A percentage is always over 100. On this case, the solution. So how do we find the pH of this? Well, we know that the pH is the minus log of the hydronium concentration, right? And we can immediately say, oh, this is hydrochloric acid. This is a strong acid. So whatever molality this is, so molarity, if we can find the molarity based on this information, then we know the hydronium because it's a strong acid. So how do we find molarity? Molarity is nothing more than moles of HCl, in this case, over the liters of the solution, right? Since we're doing percentage, all we have to do is 1.85 grams of HCl. We just change it to moles. 1 mole for every 58.5 grams. Is the molar mass of HCl, right? No, actually, sorry, that's wrong. I was thinking NaCl. So this will be 36.5 grams per mole. So 36.5 grams per moles, right? So you find the moles. So all you got left to do is find the volume. So how do we find the volume? Well, we have 100 grams of the solution, and the problem is telling us that the density is 1.01 grams per milliliters. So given 100 grams of the solution, I can find the volume by using the density, right? 1.01 gram for every 1 milliliter. And then all I have to do is change it to liters, 1 liter over every 1,000 milliliters. So once I do that, that will go there. And all I have to do is pH equals the minus log of this operation. So once you do that, once you find all those numbers, all you do is just do the minus log of that. So a little bit more challenging than the other ones because you have to use what you learned on chapter 14, how to go from mass percentage to molarity. You have to realize that you're dealing with a strong acid, which means you can assume that the molarity of the hydronium is the same as the molarity of the acid, and then you just calculate the molarity. So this is an excellent question for our test because it allows us to see how much you learn from chapter 14 and chapter 15, chapter 14, chapter 16, and 15 all together, and now chapter 17. So with that said, here's a daily work that you can do with 3 different situations. One of them including what we just did, percent by mass. And that brings us to the end of this section. So when we come back, if you notice, everything we did up to this point to find the pH was using a strong acid. So when we come back, we're going to see, so how do we do it with weak acids? And you're going to have to go all the way back to chapter 16, ice tables. So we're going to find the hydronium concentration by doing an ice table if we're dealing with a weak acid, which creates an equilibrium situation. So until the next one, see you soon. This will be the last recording of this chapter.